Three, two. All right, we're on. Hey, Jan,
All right.
good to see you again.
Nice to you.
As always, we should do this, once a week. No, just kidding, just kidding. Uh, so I want to get right into this because you've written this paper, and I take it like a white paper because it's essentially a position paper, but
Yep.
given what I know about you, I mean, I talked to Rich Sutton in the last 6 months, and he and I think Danny Silver had written a white paper on is reinforcement enough or something like this, and I was just kind of saying no, I didn't think it was, but they didn't really have much detail in it. And the thing that you did here, which I think is both extremely useful and probably dangerous at some level, is you were very detailed, right? You gave a lot of detail, and so your position is clear, and the structure of this is clear, and it could actually, I mean, I don't know how to build it, but I can see that it's a blueprint of some sort, which is really important for what's going on in the field. Now, on the same land, there's some stuff here I want to talk about in terms of cognitive psychology because it seems like you and Yosha, and of course Jeff has for a long time kind of incorporated cognitive science, and cognitive psychology in particular is becoming
Yeah.
more relevant. Now, what's happened though is our friend Gary Marcus, and I'm afraid I'm going to have to talk about him because he wrote something about this paper, and then you and one of your colleagues,
Jake Browning.
Browning, yeah,
Yes.
wrote a very nice sort of prequel to whatever he wrote, and
Right.
he kind of revealed himself even worse in this thing. But I want to talk about that because it's important because there are so many misconceptions per line in his description of what you guys are talking about, and also misapprehensions of what everyone else is doing. So
Sure.
I think it's important to get that out one way or the other, and you have. But unfortunately, in real time, he seems to have more outlets or something. I don't know what it is. He's just like everywhere.
Well,
But
he writes very well.
and he and
Let's just give him that.
that's his talent. His talent is writing things, but it's a debate tactic mostly. He doesn't really have much to say because, of course, he's never built anything, and he wouldn't really know what that meant. And he's barely a cognitive scientist, so I'm just not sure if it's. But I think it's important because there's context in here that won't make sense otherwise. Okay, so let me see if I can really summarize everything in like a few sentences here. So one way to look at what's been happening is that deep learning has solved a lot of important problems through classification. I mean, the protein folding thing is always on my mind, mainly because for 30 years, the match in terms of 3D structure was 40%. Maybe went up to 42%. And then within 6 months, it was at 98. Now, that's got to just, pause your mind for a minute, right? And then forget about all the kind of visual object recognition that's going on or classification work, sometimes with very few exemplars and very diverse category sets, still just dramatically better than anything else out there.
Sure.
But there is diminishing returns here because obviously the architectures are becoming sort of the programming language. Where do we go with all these architectures? It's just not sufficient to just add more hidden layers and make it more narrow or more deep or whatever. It's just there's got to be some principles here. So someone like you and Yosha and others should write down something, and you did. And the topic here that struck me as important is the idea that we're talking about a system that has some moving parts, but we know things already about so if this had been done in 1970, right, this really couldn't go anywhere because there wasn't anything that worked.
Sure. Yeah.
And I think this is part of the misapprehension of Gary Marcus. He likes to talk about these hybrid things, but I was in the 1970s. I remember Doug Lynette and all the symbolic stuff. They didn't work. They just did. They said they spent $50 million on the thing down in Austin, which Bobby Inman ran for years, and
Yeah.
You know, Doug's psych didn't work. It was supposed to have common sense in 2010. A lot passed, but way before that, psych never got intelligent. So I think there's a, you know, Gary and others are underestimating the value, sorry, overestimating the value of symbolic methods. I mean, if there was a successful symbolic AI right now, I don't know. I guess I might say, sure, let's explore how they can. But there isn't one. So it's not like there's something working that we can attach something working to. No, we got something broken and we're trying to attach something working. This seems like a bad engineering idea, right? I'm going to drag your car around even though it's broken. That's not a
Right.
good solution to anything.
Well, also it depends a lot on, what's your definition of what's symbolic. So it seems that depending on the time of day or the weather, different people or people like Gary will give different definitions for what really constitutes a symbolic system.
Correct. So,
So,
moving target.
perhaps, for some people at least that are interacting on social networks or perhaps for Gary, I don't know, if you put a little bit more structure in neural nets that we currently have, then it becomes symbolic spontaneously.
Right.
So he can declare victory because now, he can say, well, I told you I had to be symbolic, and you see, your architecture now is symbolic.
Right.
So he's kind of done this with the proposal that I make in that paper. So there's two essential ideas, or not ideas, but like proposals. The ideas are older, but the sort of putting them together is really what's the thing. So one of them is you need, if you want intelligent systems, you need a way for them to basically think about things in a unbounded number of steps. So it's not like you're propagating through a network or even running through a recurrent network. You are sort of inferring a bunch of latent variables that could constitute, for example, a sequence of actions. So then that turns this type of reasoning at a conceptual level. This type of reasoning is minimizing some energy function, right? So you have some criterion you want to satisfy. What sequence of actions should you take to minimize this criterion? And that starts looking very much like optimal control, classical optimal control.
Yep.
But then for this to work, you need to have some way of predicting what your sequence of action is going to result in. So you need a model of the world. And again, that's not a new idea. This has been around since the 50s or 60s for optimal control. And people have had the idea of running those world models for decades,
Yep. So I'm just putting out the model.
All right. Yes.
So now sort of what you're talking about is this structured system, which is attempting to make some kind of predictions about the interaction with its perceptual action outcome world representation. So this is it's a complicated story if you look at it. And so most of these stories, if you go back, you mentioned Kenneth Craig, Phil Johnson Laird also had this idea of a mental model. The problem was that none of these had any computational basis. They were simply kind of ideas. And yeah, probably we have mental models, but after a while, it just becomes a mental muddle because you don't really know what it's representing. You don't.
Right.
And the nice thing about this, I think one of the strongest things I can say about your presentations, I've read a lot of these, by the way, in the last year, is that your theories are almost by design. And so almost the way I put it, theory by design. In other words, you're putting the structure there so I can see the theory and I can, say, well, I'm not sure this is, honestly, I would put the world model in the cerebellum. That's just me. I just say that the cerebellum is becoming kind of the thing in the last 10 years where everyone believes that's where we simulate the world. Used to be where balance and motor systems and all that stuff, but now it's pretty clear it has all these cortical connections and also to prefrontal, so it's consistent with what you're saying. But the cerebellum sitting there, it's actually just a phase off from this moment, and it's predicting the next thing that's happening. And you see this in macaque when they do various kinds of simple visual object recognition tasks and so on, or motor tasks. the cerebellum just sitting there modeling it. And when there's an error, other areas start coming into. So it has the same flavor that you're talking about in terms of what we seem to understand about brain structure, and the way it works. And so that's kind of cool in its all own right. But then inside of this, obviously, this is metaphorical in its form. You then specify all these other structures that I'm not connected enough to know if these are all brand new, but they all look brand new to me. So, if, and if I was, doing contemporary neural networks or deep learning right now, maybe I recognize some of this, but I don't. And so it seems like you've just put down, really like a whole set of recipes that people haven't really seen before. Is that fair?
It's fair. I mean, I'm a fairly practical guy, so I tend to go from trying to kind of put together a system or an architecture, and then the theory comes later, or at least the concepts, perhaps.
Right.
Would come later. I mean, so there are a few things that seem completely obvious to me, which is that high-level type of reasoning that we observe in humans has kind of simpler versions of them in animals. So animals are capable of planning. A dog can plan very complex actions. And the dog and certainly a cat have predictive models of the world that allow them to predict the consequences of their actions in advance, imagining what's going to happen if they jump on something or whatever, right? To some level. It's not very high level, it's not very abstract, it's not very long term, it's not very, to the same level as humans, but they certainly have this capacity.
Cats spend a huge amount of their time observing you, and that's pretty much all they do. They're watching you so carefully, and they can predict where you're about to go, what you're about to do, and if you violate that pattern, they are now upset.
That's right.
And they
will
can
be very surprised if you play tricks on them, right? So it's pretty obvious that we need, if we want any kind of intelligence, we need some predictive model of the world that will sort of allow us to predict in advance what's going to happen in the world, because the world is being the world, or because of an action we're taking, or a sequence of actions we're taking. Okay, so now that's that's a necessity. It's as necessary as, back 35 years ago, when we were thinking about, how do we do pattern recognition? Well, it's pretty obvious that you have to extract low-level features and then, build a hierarchy of more abstract and abstract features, and that's where deep learning comes from, right? That's the whole idea of neural nets. And then you will have theories that tell you, I can approximate everything with 2 layers, because, with kernels, so you don't need deep learning. And you have to tell them, you have to explain to them why they're wrong. And so there's a similar thing here in the context of autonomous intelligence, which is, theoreticians from reinforcement learning that say, I can prove that reinforcement learning model 3 will converge.
I like that. I like the return back to models and that getting away from model 3. I thought that was a really important point too. But before you go there's something you just said that it's bothered me for a long time about sort of the standard story in neuroscience that also gets, I think, adopted in machine learning, or certainly neural networks, is the idea that you take sort of Hubel and Wiesel level edges, and then you build something in V5 that's more complex, and then something. And then if you look at any standard neuroscience textbook, you'll see this huge gap between the edges and some patterns, and then faces. And of course, these are the kind of features that are obvious. We know there's edges and we know there's faces, but these intermediate edges have sort of all the information in them. And we don't know what they are. And I think actually there's some really nice work going on in visualization with a couple of different groups. I think Chris Olot maybe is his name, and they're doing some visual. And what they're finding are these, I would call them like chimeras that seem to do multiple pattern matching, and they're at this intermediate level. And have we seen these in the brain? Yes, we have, but no one actually talks about them because they don't know what they are. And I believe that this is something that could be exploited in deep learning kinds of results, saying, well, what is this intermediate layer? You remember there's the old idea of, Biederman and other people had geons, and they'd say, okay,
Yeah,
we
yeah,
can
yeah.
build these structures. The problem was you could recognize dogs from cars or dogs from, something else, but you couldn't recognize within that category dogs from dogs. And that's the problem with a lot of these primitive feature models coming from cognitive psychology originally. They just couldn't, really fit the data, and no one knew what the intermediate set was. I think buried in deep learning models, in the ones that are very successful that are already learned, you go and mine those, you will find these intermediate structures. And
Yeah,
they're
I mean,
probably going to
that's
be
still
very
what a lot of
important.
people are doing, right? I mean,
Yes.
there is, literally hundreds of papers now
Yes.
in visual neuroscience attempting to explain observations for either fMRI or electrophysiology.
Yeah.
And the model with which you explain it is a convolutional net, right?
Yeah.
So,
Yeah. Yeah.
and people have done this also with transformers to explain like how people understand text. And so there's work by a colleague at Fair Paris called Yann Le Cun, and he's done this kind of stuff. Shown that there is also kind of hierarchical levels in sort of text understanding, essentially.
Right.
And you can correlate that with the various levels in the transformer, but
Absolutely.
So that's a big progress, because 20 years ago nobody could tell you what the hell V4 was doing.
That's right. That's right. And I think I think there's still a lot of shoes to drop here that will shock neuroscientists a lot in the near future. Let me go back to the process model, which in effect, it's sort of like well, the difference between classification of object or type versus action classification. So there's a sense in which part of what you're focused on is the action and its consequence. And so there's an older model here. I want to just put that up here. That's due to, and you probably know it. It's due to Ulrich Neisser from like 1976. Maybe you've ever heard of this. It's called the perceptual cycle.
Okay.
And you're going to recognize some parts here that seem familiar to what you did. Now, this is obviously a little tight. It has no computation here, no mechanism, but the concept, I think, is fluid with what you're trying to do here. So here, the idea was that there was some kind of sampling in the world, some perceptual information, and this would produce some kind of outcome. So the example would be, you're standing by your front door and you see some boxes. So there's some boxes arrived, okay? So then you go down here to the schema level, and you have the schema for front door. Yes, boxes can come to my front door, so that's okay. And then that comes back. So you search around for more boxes, and so on and so forth. And this cycle continues. Now, of course, if you find a car at your front door, this is going to be surprising at first. And then you find out there's a note in there, and your neighbor got drunk and they drove over your lawn and they end up at the front door. Well, that produces, again, a sample and this change in the schema. And now you have a car at your front door schema that you didn't have before. So this is actually a learning process. And you can see in like children where they might encounter something as a perceptual sample, and then they move to modifying and building these schemas. Now, this, I think, is something in your model already, but the schema thing was something that would be in long-term memory that would be pulled out of short-term memory, and then it would be basically have almost like a slot filler structure, like a script that would say, well, I'm expecting something to happen, and then you go look for it, that directs the cycle, and then you just got this virtuous cycle goes around it. And this sort of held sway for decades about the way in which this kind of explicit processing occurs. But there's also implicit processing here in that you actually identify something, but you may not know what it is, or you may not have a verbal description yet. So a lot of cognitive psychologists will say this explicit modeling, which Kahneman was talking about as system 2, is really this thing where you're using some kind of language, you're using some kind of representation, which you can communicate. Whereas the system 1, as you say, is so much simpler, and has this immediate kind of action perception.
Yeah.
So this is I think this is interesting in respect to what you're doing as at least some kind of bridge back to this kind of thing. And this is something that is related back to the cerebellar prediction machine. Is the idea that you're simulating the world, sort of phase off some amount of time, maybe I'm going to guess 500 milliseconds, and then you make a prediction, and that moves you forward. And your world model is really these schemas. So that's kind of what I'm trying to see if that's something in your model. These schemas are really little bits of category structure that allows you to organize things before you've seen it. And again, if you're a child, one good example was when we took our son to expensive hotels, he'd find under the pillow some candy. And then when he went to a Hotel 6 once on the road, he said, "Where's the candy?" There's no. So his schema basically had to be updated, but then he had to create certain kind of causal structures to do that. And that's why I thought this might be relevant.
So I don't know enough about the cerebellum to really tell if it constitutes a world model. I think it probably does very short-term predictions. So maybe, as you said, a few hundred milliseconds or something like this. Perhaps what it models better is our own body as opposed to the environment.
Well, no. More recently, it's also the environment.
Okay.
You're right. You're exactly right. The cerebellum was a model of proprioception and kinesthetics of the body. But no, what people have discovered is the cerebellum seems to be a little simulator brain sitting there watching everything you do and then predicting it. And so it has that quality of what you're saying.
So my guess is that it's short-term prediction, and then there is a much more complicated problem to solve if you want to do long-term prediction, which is that you cannot do fully accurate, complete long-term prediction. You have to, if you want to make long-term prediction, you have to make prediction in sort of an abstract space of representations where the details are ignored or not present. And so your prediction might actually be accurate if not as detailed, right? So for example, you're driving down a road and there is cars around you, might be pedestrians on the side that might decide to cross the street, blah blah blah, right? You might want to be able to kind of predict ahead what's going to happen within the next second or so if you want to plan a trajectory for your car that is safe. But then if you're trying to predict every detail about the world, you're going to have to predict the random movement of the trees and the leaves of the trees that are bordering the road, and you'll end up spending all of your resources predicting stuff.
You have to know what to throw away.
That's completely unpredictable, right? So if you want to do a good job at predicting, you have to basically abstract away, eliminate from your representation all the irrelevant details about the world.
Exactly.
It's even like the longer term prediction you want to make, the more details you want to give up. So for example, if I want to go from New York and visit you across the river in Newark, I can guess, the steps I have to do is go down to the pass station and cross the river and maybe walk or catch a taxi or something, or take the train from to Penn Station or whatever. But I can predict, or if I drive, I can predict roughly how long it's going to take and what the waypoints or the stops are going to be, right? So there's a sequence of like 4 actions, macro actions that I know I need to take, and roughly it's going to take me 45 minutes or whatever it is. Now, if I go down one level, the first level is like, I have to go to the pass station, for example, which is kind of a light train for people who are not in New York. I have to get out of this building, walk down the street, get to the station, blah, blah, blah. To get out of this building, you have to remember where the door of the elevator is, and then all the way down to millisecond by millisecond muscle control, which there clearly involves the cerebellum.
Right.
But the high-level planning probably takes place more in the sort of prefrontal cortex.
Well, they interact, and there's definitely
Yeah, of course they
there's
interact.
definitely- and the medial temporal lobe is actually where all that long-term storage is. So if you start coming over here, it turns out they're filming a movie over here in Newark, right outside the subway station, and it's a zombies movie. So you're going to be really surprised when you walk out of that subway station and you see people walking around who look like dead people. Well, so you have now a new schema, right? So that's the whole point. If the subway car slows down just before it gets to the end and the conductor comes out, there's something wrong. That's a schema you've had before, but for all those Zoomers sitting on the subway, they're going, why is it stopping? So now they've acquired a new schema. And so it's similar to that kind of, the prediction failure produces another sort of long-term memory structure. And then the question is, how do you put them together? I mean, one thing that's not well understood in cognitive neuroscience is this interaction between this implicit, explicit structure. How do we get stuff that we know how to do and turn it into representations that are verbal and conscious, to use the C word, the dangerous C word. So there's conscious awareness that says, okay, I'm aware of this stuff. Whereas if you're just getting on the subway and going somewhere, you really don't build a huge conscious awareness of it. If you've done it 1,000 times, you just do it. And this is a problem, because those two kinds of functionalities do seem to be separate in the brain. The striatum is where a lot of that implicit stuff is, medial temporal, but they're close together. And there is some research that shows how they interact, but mostly it looks like they avoid each other.
Yeah. So it's one thing I talked about in the position paper. There is the sort of deliberate, system 2 type planning, where you use a world model and you only have one world model or configurable engine to run your world model in your head, which means you can only focus on one conscious task at any one time. And then you use the full power of your predictive power of your world model to be able to plan a sequence of actions to arrive at a particular goal. But then once you have this optimal sequence of actions, you can either take the action, or you can also train sort of a direct predictor to predict, in this situation, here is the action I should take. And so the more you do this planning in the field, the more it gets compiled into this sort of direct policy, which subsequently you don't need to think about to execute. So this is the schema acquisition you're thinking
yes,
about.
I think that's
you learn to drive, and you're like completely focused on the task, and you imagine the catastrophe scenarios, and blah blah blah. And then after 50 or 100 hours of practice, you drive without thinking, and people can talk to you and stuff.
That's right. Well, it's also that notion that you've got this one world that you're dealing with at a time. Right?
At a time.
There's an attentional process that sort of encapsulates it, then that says, okay, this is what we're doing. And breaking that then in fact breaks down something about the prediction. In other words, the relationship between attention and prediction may be a lot tighter than we imagined. And I think that's implicit in your model, but I'm not sure. But this is the thing that's always confusing. Why is our attentional capability so narrow and so fragile? And it might have to do with this optimization process that's costly. Obviously, the more this costs and the more energy you're putting into it, you better do it, right? And so trying to pay attention to a bunch of things, which obviously we can do, lowers the chance of making a high quality schema at the end of this, perhaps.
Right. So the hypothesis I formulate is really speculation. Is that we only have one engine in our mind for the world model, and we configure it for the situation at hand.
Right.
And so this is configurator module on top of everything, which is supposed to sort of configure the rest of your brain for the task you're currently solving. and which is why you can only solve, you can only attend to one task, conscious task at any one time, because you only have one engine.
Right.
Okay? And there is an advantage to this, a computational advantage to this. First of all, this engine can be extremely powerful because you can basically occupy half of your brain. But also, you can share knowledge. Because you only have one engine and you only reconfigure a piece of it, you can, whatever knowledge is acquired to be able to learn your world model can be transferred to different tasks. If you had a separate world model, completely separate world model for different tasks, then you would have a hard time kind of using knowledge you learn in one task to kind of transfer to another one.
And it might not generalize in the way you'd hope. Yeah.
That's right. But perhaps if we had a much bigger head, we might have multiple world models that would allow us to execute multiple tasks.
I think there's something sensible about that, but and the mechanics you're describing might be the constraints. But it is clear that our attentional resources are limited. Short-term memory is not as large as you would imagine. So we can barely get 9 or 10, maybe less than 7 chunks in there, as George Miller used to say. But there's something about that gets optimized while it's happening. Now the nicer thing says these schematas are the things that are holding your attention, and that's I think that's similar to some of the mechanics you have here. Is that schemata is basically demanding you pay attention. It's expecting something to happen. You're sitting in a restaurant, a menu should come, a waiter should appear, and the longer that happens, we have prototypical durations, right? If you're sitting there for 20 minutes, there's something wrong. Yeah. If they come there in 5 seconds, there's probably something wrong. There's always some kind of characteristic unfolding of these schematas that relate back to the causal structure. Now, this is also why, of course, causality is so difficult, because obviously this is a perceptual memory event. We can't really test causality in these simulations.
Right.
We can predict things and they can fail or not fail, but that doesn't mean they're causal yet. That just means we have some associations, and that gets me to your JEPAs, I think. But before we go there, I did drop something here that I wanted to go back to the Marcus mess and talk a little bit about symbolic processing, because he confounds a neural network using just its own, intrinsic piece parts to do mathematical reasoning or reasoning about an opera or something like that as symbolic processing. And indeed, it's processing symbolically, but in a way that isn't using some kind of computational artifact, which is symbolic. And he just quickly confounds these all the time. And that essay, it gives you a headache as you read it. I think that's part of the problem. But clearly, the kind of systems you're talking about here can do symbolic reasoning in the sense that we'll be able to, and here's the hard part, we'll be able to communicate it in some kind of language. So whether or not we think of the transformers and all the dollies and whatever they're doing as an important part of this, I don't care. But clearly there is something that will have some kind of semantic structure that two AIs will be able to communicate without sharing common computational systems. And so that's what gets interesting, is how
the linguistic aspect of it, or the communication of thought, for me is, number 348 in the list of 500 items, in the sense that, we're not even close to reproducing the kind of intelligence and learning abilities we observe in cats and dogs, and they don't talk, right? So let's get that right first, right? And they can plan, they can reason, and they can plan, they can predict. And because they can predict, they can plan. So let's get that right. Now, whether planning through minimizing some objective function with respect to latent variable that represent action sequences, whether you qualify this as symbolic or not, I really don't care. If you are, Gary Marcus, you might want to declare victory and say, aha, now Yann Le Cun agrees with me, you need symbols. But really haven't changed my opinion on anything. This is it's neural nets, and there is an underlying principle in there, which is you don't run through a bunch of feed-forward layers. Through gradient descent, optimization, search, whatever you want, you kind of find a configuration of unobserved latent variables that explain what you're observing or predicts or minimize some objectives that you want to satisfy. This is similar to what you do in Bayesian nets and graphical models, right? You have a bunch of nodes and variables and dependency between them. You know the value of some of the nodes because they're observed, and what you need to do is infer the most likely combination of values of the other ones through maximizing likelihood, which is like minimizing of likelihood, negative likelihood. So this principle of imputing, latent variables through minimizing some cost function is a very old one. It's not a new concept or anything. Right. But I think it's an essential component. It's a good way of getting basically neural systems to exhibit some form of reasoning. And the interesting thing is that essentially none of the large, presumably, top of the heap AI systems today do this. They don't. Like the big transformers, the GPT-3s of the world, all of those things, they don't have any latent variables that they infer over. You just run through a bunch of layers of a transformer or a cognitive vision, whatever. And then you make a prediction, you sample from some distribution, and then you kind of do this ecosystem.
Yeah.
But there's no reasoning, there's no inference, there's no abstract latent variable. That's what you need for.
I said something like this to Jeff when we were talking. I said, well, it seems to me this is just like some big lexical blobs that are out there, and you probe one of them with the right vector and something pops out that has some similarity to it. And it's a Rorschach test after that. I mean, there's no way to actually verify that this has some relationship to some larger semantic space. And Jeff said, I disagree with you. I think you're wrong. And I think we'll find that in fact there is a causal structure to these things. So I mean, he was all about Dolly at that point too. I mean, no, that's fine. I said, well, I still think it's a blob, but the point is, and then we also argued about whether or not you could actually test this in humans. I said, yeah, okay, so it's just as bad as humans. You're right. I can't test it in humans either. So what? That's wrong. But okay. But this gets back to this thing. What do you think this thing will do? Let's suppose, and you've got more resources than I do. You can actually build this thing and put it into a robot or put it into some system and start to tinker with it. It seems to me. I mean, it does seem to me that you can find out things. Now, what would you expect, a robot like this to do? And by the way, I'll give you one example that I think is incredibly impressive. I don't know if you've seen this Boston Dynamics demo on YouTube, but it's essentially all they did was put a gyro in one of their dogs and then erase all the code and probably put a unsupervised deep learner into the thing or something that did unsupervised learning. And all it had to do was get the gyro to go up. That's all it had to do. Now it has 4 articulators that are very complicated, and the thing starts to bat on the floor, and with about 45 minutes it's standing upright and walking around. Very similar to a calf being born, falling out of its mother's womb on the floor, and its legs are bobbing around, and all of a sudden the damn thing's walking. And this I gotta say, out of all the other things I've seen, I thought this was the most impressive. And they did it in real time. It took an hour for the learning to happen, which is probably right.
Yeah, there's some work along those lines at I think it's collaboration between Berkeley and FAIR actually in California. So it's one of those robotic zones, and it plays around, and it's going to learn
and
something.
then it starts walking. And I think it also gets at this issue of, how much knowledge do you need? Well, look here, all you need to know is that you're an upright gravitational field, and you want to be up,
Right?
and and you don't need a lot of samples to do this.
Well, so I mean, ultimately, I don't know if this is the complete blueprint, or at least a conceptual, notional blueprint for, perhaps a robot with sort of the level of competency of a cat or a dog, right?
Right.
But that's kind of where we go. So there's a lot of critiques, on the social networks and various media that say, oh, but your model doesn't even talk about language. And language is essential to human intelligence. Blah blah blah. So Jake Browning and I wrote a piece recently saying that what the kind of knowledge that we can express with language is actually kind of a relatively small portion of all of human knowledge. Like most of it is completely subconscious. We take it for granted. We don't even, think it's important. Like, this is one reason why perhaps in sort of classical AI, the complexity of tasks like visual perception was sort of somewhat underestimated, at least initially.
Right, that's right.
Because we kind of take it for granted, but it turns out to be really complicated, and it occupies like a quarter to a third of our brain, right? So,
right. Well, that's the disconnect between explicit and implicit. I mean,
and implicit,
I can play tennis, and I can tell you how to play tennis, but you're not going to learn it unless you get that implicit. You play it 150 times, right? So
that's right.
That and then you can describe it to someone else, and that's what that's kind of the weird disconnect here is between that language explicit structure that's conscious. Mm-hmm. I'm telling you about it, but there's no way you're ever going to be able to do it unless you go do it, and that's why there's something still missing here. I'm not sure what it is, but there's something between those two states of knowledge, and you're right, language doesn't solve it. You can't just give it language and okay, that's gonna no there's something very important about the way language interacts with these implicit structures. Sure. And the nice thing is, of course, Deep Learning Circuit 2022 has solved, and I'll say that in a strong way, solved a lot of these implicit learning problems. The thing that Gary Marcus and all of his little trolls are missing, they don't get that that was a hard part. And not to say that anything else isn't hard. I'm just saying, I think you're right. You have to start from a place where you actually know you can stand on the ground before you start building things. And this is so it's almost an appropriate time. I mean, again, it's still early, and I suspect you're going to, this will evolve very rapidly as you start to do stuff with it.
There's no question, and maybe some parts would be, subject to major revisions. That's where maybe we should talk about JEPA. So JEPA is this architecture where, you can imagine an intelligence system training itself to understand how the world works by basically training to predict, right? Predict what's going to happen. But the problem I was explaining earlier, you're driving along the road and there is random motion of the leaves on the trees. You don't want to be predicting this. You don't want to be spending any type of resources predicting random motion of the leaves or the wave on a pond or something like that, right? So what you need is not predict all the details of what happens in the world in the pixel space. What you want is kind of lift up to a representation space and make predictions in that space. And that's what JEPA is. So JEPA means joint embedding predictive architecture. Joint embedding because you take, the video clip of the world and then the next video clip of the world, what happens the next few hundred milliseconds or something. You run them through encoders, and then in that embedding space, you're making a prediction. Now, so this looks like what we used to call the Siamese network, right? Siamese network, you have two identical networks, and you feed them with two different views of the same object, for example, and you tell the system, well, you should have the same representation because those two are two different views of the same object. And those things have actually encountered a fairly large amount of success in self-supervised learning applied to computer vision. So the best self-supervised learning methods for computer vision today are using joint embedding architecture. So using basically variations of the old idea of Siamese nets. With different criteria. That's the thing. Now,
one thing that's confusing me, just to go back a little bit and unpack it. So, right, we want to ignore extraneous variables, and so the wrestling leaves that. But moving to that abstract layer, I'm not entirely following how that removes the extraneous variables, right? Because there's a lot of superstitious behavior in the world,
Sure.
and it's partly because we got captured by those extraneous variables, and
Well,
so
because we also suck at causal inference, but
yeah, exactly. So
okay. If
why
you
does
have an
that work?
encoder, right? You feed you have two observations. Let's call them x and y.
Right.
You could have a generative model that predicts y from x. But the problem is there are many y's that are possible that will correspond to an x. So let's say x is a video clip, y is the subsequent video clip. There are many y's that could be continuations of the original video clip. So if you train a prediction system to directly predict y, it's going to have to make one prediction, and if you want to predict the video of me right now, you could predict that I move my head to the left or to the right. But if you have to make one prediction, you have to predict the average of all the possible motions I can make, and that's a blurry version of me.
Right.
So that's not a good way to do this. So then, of course, the answer is the standard answer in machine learning is to say, well, we're not going to make a point prediction, we're going to predict a distribution. But like, how the hell do you represent a distribution in image space? We don't know how to do that. It's just high dimensional and it's completely hairy, right? Okay, so the idea of JEPA is you embed Y as well. You run Y through an encoder, and this encoder has invariance properties that will make it eliminate a lot of information from the input, hopefully not the relevant one.
So
and prediction in representation space. And the main issue you have to deal with there is the same as with Chinese net. You have to prevent the system from collapsing, which means you have to have some way of telling the system, keep as much information as the input as you can. You're not allowed to just make your representation 0 all the time, which would, of course, make it easy to predict, but will make it useless.
Yes.
The big question, and that was the missing piece I've had in this entire, grandiose plan for years, if not decades, is how precisely you prevent this collapse. And there is a proposal in the paper. It's a technical VCREG or VCREG.
Yeah, VCREG. Right.
Do this. So it maximizes the information content basically of the representation while at the same time making it predictable.
But the causal part of it is still eluding me, because I can see how there could be some filtering properties. Now, and so this thing is going to be iterative. It's going to converge on something. Doesn't encode immediately, and now it's going to have to keep doing this, and eventually it's going to find that ignoring the leaves on the tree when you're training the car is probably useful, because there's a constancy or there's a lack of predictive integrity between the things out there, and so it determines that through trial and error, through what I mean, isn't this at some point somebody is going to get captured by the wrong thing and assume, I see this all the time, by the way, when the people are driving, they're turning left, and they've learned incorrectly that it's some kind of ballistic motion, so they turn right a little bit as though they have to ease into the left, but of course the car is non-holonomic. It will do that because that's what they do. And just because your body feels better doing that doesn't mean the car feels better. And in fact, you're probably going to hit somebody in the right lane if you keep doing that. But that's the problem. That superstitious behavior is all over the place. So it's like we have a lot of bad JEPAs in our heads.
Yep. I mean, to some extent, your level of intelligence or your capability, your ability to survive is related to the accuracy of your model of the world, right? So having a bad model of the world is a very
dangerous,
stupid.
So I worked for many years in animal animal behavior and animal research, and did a lot of animal studies, and I was very interested in exactly the kind of things you're getting at in terms of reinforcement learning and the nature of this kind of thing. One of the things that we once published in a science paper back in the 70s, and it was called Causality in the Pigeon. And we did this really simple experiment. I think it basically is related to JEPA, so bear with me when I tell you this little tiny experiment. You have a pigeon in a Skinner box. There's three keys in front of you. The middle key's white, and you're the pigeon, you're pecking in the middle key. And every once in a while, the keys will turn red and green, the white light will go out, and then you pick one of the sides based on a criterion, and then you get fed if you're correct. Now, here's the criterion. Unbeknownst to the pigeon, there's a computer algorithm that's pecking along with the pigeon that has been watching it very carefully and models the distribution of its pecks. And it's pecking at about the same rate as the actual pigeon. And sometimes then there's an anchor standard, which might be 100 milliseconds, it might be 20 milliseconds, at which then the artificial pigeon causes the change and the real pigeon doesn't, or vice versa. If the pigeon that's really pecking on this side thinks it caused it, it has to peck the green key. If it thinks it doesn't cause it, it has to peck the red key. Now, animals learn this within a couple hundred trials. They would get really good at it. The problem is sometimes we'd set up where the distance, we'd do a psychophysical function where it would be 10 milliseconds, 50, 100, and so on and so forth. And sure enough, there's a criterion where the JEPA, if you will, breaks down. So if you get at 44 milliseconds and below, the pigeon will just say, I don't know, falls to chance, and it just picks the key randomly. If you're anywhere above 50 milliseconds, the pigeon's 90% correct and always detects whether or not the artificial pig is paying. One day, which often happens in these cases, the key got stuck. So as a graduate student, I went in there to unstick the key, and there was a little piece of seed in there that the pigeons would knock the seed around and get up with it. The little seed there. And the pigeon was over here watching me, and I clicked it out, and sure enough, the lights went red and green, and the pigeon ran across in front of me over to the green key and said, I didn't do it. It was him. Or the red key, sorry. And so the point is that it knew that the causality was correct simply because it had generalized. The thing that surprised me, since we were just doing temporal psychophysical estimation, it generalized from that to spatially me as another object in the room, another animate object pecking the thing, and it did that so quickly. So that's a problem. I mean, computationally, it's an interesting problem because it always struck me as, how the hell did it make this causality decision from the time basis to an animate object in space so rapidly? Because there were no trials.
I mean, I think for a lot of animal species, probably they don't need to intervene in a situation to establish causality. They can observe other agents and establish causality through this observed agent.
Right. So there's this kind of imitation learning kind of thing. And
it could be imitation learning, or if you're just learning a model of the world, you're not trying to accomplish any task, right? So you're not doing imitation, but you're just trying to establish what is the kind of causal effect, and you're not the one taking the actions. You're just observing another agent taking the action.
Right.
But I mean, humans are not particularly good at this.
No, they're not. No, they're not.
This animism and basically all religion is based on mistaken ideas of causality.
We're going to get in trouble, but yes, and that and lesions in the temporal lobe. Those are the two things that cause religion, as far as I can tell. But the interesting thing about that time thing, it appears that our sampling rate in terms of processing information, let's say from V1 into prefrontal, is around 100, 200 milliseconds. Okay, so in that period of time, not much is going on. But that psychophysical time, people have tested this also in humans, is right around 40 milliseconds.
Right.
And so that's another disconnect, because there's going to be, some kind of mismatch between what I perceived and how I filtered it and how quickly I have to say I caused it, or somebody else caused it, or it got caused out there. And so there's a lot of possibility for capture error, and this kind of superstitious behavior, I think, is a common kind of outcome of this in terms of at least human behavior. But I can't I can't explain all politics and the odd behavior of our political constituencies by all this, because that's much more complicated. But in any case, this is I'm gonna I think I had yeah one thing that you brought up was this hierarchy thing, and that was the last thing that caught my attention in terms of the structure of this thing. Because of course there's lots of hierarchies, but there's also, I mean, if we pander towards neuroscience, there's a whole lot of feedback, and
Sure.
there's a whole so anything that's happening in object recognition is obviously I see something, and then my visual areas feed it forward, and then the prefrontal cortex pushes back, and then there's a kind of a negotiation, and finally we all agree what we saw. And that's something that's still kind of missing from a lot of, the basic modeling at the system level, and certainly at, in terms of just standard classifiers, which are all feed forward.
Yeah, absolutely. So the way I talk about hierarchy in the position paper is to attempt to propose a potential solution to the problem of hierarchical planning. So it's related to this idea I was talking about earlier, that the more abstract representation of the state of the world you have, the more you're able to make long-term predictions that eliminate all the irrelevant details that you cannot predict anyway. And then, as you go down the hierarchy, you make shorter-term predictions that are more accurate in the details. And the question is, what's the interaction between all of those different modules? So if you want to do hierarchical planning, you have a high-level model of the world that tells you, I can go from New York to Newark, in about 45 minutes. If I go to the path, whatever.
Right.
And I can decompose this in a set of criteria that have to be satisfied. You can think of them as cost functions.
Yeah.
As surrogate cost functions.
Right.
There's one cost function which would be like, how far am I from the train station that I need to take, right? And so I need to minimize that with respect to lower level action variables. Going down the street, walking to the train station, and then going down the street, I have to kind of decompose this again, and kind of go down. So that's perhaps one semi new idea in this paper, which is how you do this hierarchy.
How you do that.
And the high levels basically define objective functions for the lower levels to plan with.
Right. So this was a problem in the nicer business, and what was called event perception, was everything at that action level is a partnomy. So it's you're going to the theater, but you're going to have to tie your shoes. You're going to have to get a cab. You're going to have to do this, and you have to pay, and the blah blah blah, and then all these little actions have to somehow be embedded into the larger action, and then they have to be consistent. And when people do event perception, they say that this is their standard explanation of what they're looking at is this. So okay, well, so I think we have probably covered the entire paper. I think
and we are out of time. I'm sorry to say, because I have to.
I know, and I was going to say I'm out of time too, and I just wanted to add this last thing, that Gary Marcus is absolutely wrong about this, and we'll have to return to this another day. And I hope your rest of the evening is good, Yann. It's good seeing you.
Great to see you.
And thanks for coming back, and I'll see you again sometime soon, I hope.
All right, absolutely.
All right, that was fun. Bye-bye.
Okay. Take care.